Chapter 9, which is the transport layer. So remember with the OSI model, transport layer is pretty much right in the middle between our more physical layers and then our more logical layers. So physical data link and network layer, of course, are being more so at layers 1, 2, and 3. And then, of course, the application session and presentation layers being up at the higher levels. So the transport layer deals with kind of stuff in the middle. So we're going to talk about how these protocols and services support communications across data networks, the purpose of the transport layer in managing data transport and end-to-end communication, as well as the characteristics of TCP and UDP, including how we deal with port numbers. We're going to look at the comparison of these protocol operations for TCP and UDP. We're going to look at how session establishment and termination processes facilitate reliable communication, because remember, TCP is the reliable aspect of the TCP IP suite. When we talk about the suite, we're talking about that collection of protocols. IP is not considered to be reliable. It is a connectionless protocol. TCP does all of the regulation at that point. We're going to look at how TCP data units are transmitted and how they're acknowledged to guarantee delivery. So we're going to talk about the handshake, things like that. We're going to describe UDP client processes to establish communication with the server, because UDP, like IP, is going to be connectionless. It does not have to be initiated and terminated in the same capacity as TCP does. And we're going to look at whether a TCP transmission or UDP transmission is best suited for a particular application. So the transport layer protocols are responsible for establishing a temporary session of communication between two hosts, specifically between two applications on two hosts, and being able to move information between the two of them. So as I said at the very beginning of this lecture, it's the link between the upper and lower layers to try and keep everything streamlined. You know, we worry about, in the TCP model, as you can see from the graphic here, application up top, internet network access below, being able to handle, you know, things in very broad categories. So our responsibilities at the transport layer are to track the conversation. We're trying to make sure we're keeping track of the individual items being processed from a source to a destination. Segmentation is going to go ahead and divide the data into segments that are easier to manage and transport. So this is part of our what we call the encapsulation process. The first thing we have to do is break apart the data into individual absorbable pieces so that we can then add header and trailer information as we progress. The header used for reassembly is going to be used for tracking, so we have the ability to not only know the correct order of operations for putting a piece back together, but we also can identify, did we receive this particular piece? Did we receive it in the correct order if that is something that we're processing? And then, of course, identifying the application. So let's say that, you know, right now I've got, on my taskbar alone, I've probably got 6 or 7 different programs running. And all applications need to be able to keep their data separate. You know, the stuff that I've got in Microsoft Word versus in Microsoft PowerPoint versus in my web browser, all of this stuff needs to make sure that it has a specified flow. You know, you don't want that data to be crossing over from one to the other. You know, don't cross the streams, as they say. So you need to make sure that these applications receive their correct data, and the way we do this is via port numbers, so that we can make sure that everybody gets their information to the correct, if you want to think about it as a mailbox, that would be a way to look at it. So here we have an example of this graphically. We can see that on the network we've got things going to an email server, or an email application rather. We've got instant messaging. We've got multiple web pages open. You know, if you have web tabs open in one browser, you have to be aware that there is a essentially a separate instance of that web browser being opened every time that you open a new tab. That's just the way that it's consolidated. And then online video chatting and streaming video, which is what we're doing now as well. So those separations are all done by means of port numbers in order to control source and destination applications. So the process of segmentation allows us to do what's called conversation multiplexing. So multiplexing is just being able to transfer multiple streams of information on the same network interface. So here you can see there are these different symbols. We've got some that have this kind of like Lego appearance to them, to where there's this like light blue at the very top with a little nub there. We've got the dark blue triangle here. We've got kind of this hexagonal shape there. We've got a circle, and then we just see how these patterns repeat. And the order is not necessarily important. It's just making sure that we can differentiate one to the other. So not only does segmenting allow us to break stuff into smaller chunks, it allows us to break them into even chunks, so that way we have what we call our MTU, maximum transmission unit. Make sure that packet size is the same as we move from one place to another. So it allows us to signal things much more rapidly because we can predict the size of those chunks. So TCP gives us two different protocol choices for transport layer. We can use standard TCP, transmission control protocol. This ensures that all data arrives at the destination. We can verify that it's arriving in the correct order. We can verify we can verify that the data is in the same format that it was transmitted as well. We can do the integrity aspect of it. So additional fields in the header may be needed in order to perform these actions, which will increase the size of the packet as well as the delay transmitting from device to device, because different things have to be processed. If we have to check and make sure that a particular item is being processed correctly, that means that we have to read the fields, process that information, and then do the acknowledgement or whatever else we have. So UDP is kind of the opposite of this. There is no reliability provisions included. Now, because of that, we are able to make this thing substantially faster. There are things that do not have to be read through. It's all about transmission. So as long as we make sure the transmission is going through, everything's square. So it's much faster than TCP. But if we have any loss of transmission content, we don't really know as the program stands. Now, we know as the user, obviously, we can have an issue with watching a video stream get kind of chunky because all of a sudden it starts getting pixelated and losing resolution. So here we see kind of the structure of these layer protocols. We go from the top at the application layer, FTP for file transfer, HTTP for web traffic, and then HTTPS, of course, to be a variant there. SMTP, POP, and IMAP for email. DNS, TFTP, all of these different things communicate. As we can see on the transition from the top layer to the next one down, the majority of these play in TCP's sandbox. Now, DNS and TFTP can work in UDP space as well. So this is important to note. Whenever we're dealing with TCP, FTP, HTTP, these are things that we do not necessarily want to lose information on. Web pages, emails, file transfers for programs, all this stuff, we want the data to arrive in the exact same shape that it was sent, right? We don't want to lose any bits, even small ones. So that's why TCP is so critical. Now, UDP, on the other hand, for something like DNS, I'm going to send you this information. If you get it, great. If not, you can send me another request and I'll update you again. That one, as we see, works in both areas. And then TFTP, the T standing for trivial, is usually going to send very small bits of information like basic server configurations, things like that, from a source server on a main website for local traffic. Once we go down from TCP to UDP at the internet layer, we see that the IP connection is there for that particular protocol. And then we get down to the LAN and WAN connections at the physical space for network access. So TCP, the way we like to think about this is it's like we're sending a package that is being tracked. If we send a shipping order in several packages, we can check online to see what the status is for each one. So if you go on Amazon or any other major purchase website for e-commerce, and you make a big order, especially if it's from multiple vendors, some of the stuff they can consolidate. They can say, okay, we're going to go ahead and send all of this in one package if possible, but there's a little box you can check that says, no, send it to me in as many packages as you need to, just get it to me as quickly as possible. So that is an option you can do. in any event, whenever those packages are sent, whether there's one or there's a dozen, they can say, okay, this particular item is in Wisconsin, or this one's in Nevada, or this one's in Texas, or this one's in Ohio, or hey, this one's out for delivery right now, regardless of whether or not they're part of the quote same order, end quote. So we can check that status. That's a big thing about using TCP. Now we can see here that we have 3 segments being forwarded out from a user. It's going through the various ISPs, goes across the internet in whatever cluster it may be, and then it will arrive at the secondary ISP interface where the delivery section is supposed to happen at the server farm. The first 3 segments are received, and the file server acknowledges this and sends back response packets. So we send, everything processes, the segments all arrive, the file server sends the acknowledgement, and it's like, okay, I'm going to send you this. Okay, I got it. Great. Let's move on to the next set of packets or segments. So the next 3 get forwarded on, but we have a problem. For whatever reason, these 3 segments do not arrive. So the system's like, oh, we have a problem. I didn't get anything. But because it's like I didn't get anything, I don't know I'm supposed to be getting something, so I'm not going to send any form of acknowledgement or whatever else. What we're going to wait on at this point is the timeout. So remember the time to live or the next hop stuff we've worked with IP packets being sent out into space. With that, we have essentially that TTL has to become active, and then the 0 kicks in, the packet dies, and at that point, the server that originated the request says, okay, we sent the packet, it's been beyond the timeout window, we haven't gotten anything back, so I'm going to assume that that particular segment is gone. So I'm going to go ahead and reset. Now, let's just say that there is a delay for whatever reason. The TTL is not necessarily the problem. It was just delayed. It had to do a different route or whatever else, and it gets to its destination. So the packet then gets accepted. At that point, we have that packet. If a secondary delivery of the same packet comes in, it will say, no thanks, already got one, and it'll discard it. So that's where that comes in. So as we can see, these 3 segments get resubmitted, they arrive, they're acknowledged, and everything's good. So in this little tableau we've done, we have the 3 primary responsibilities for TCP. We are going to number and track data segments as they're moving across the network. We're going to acknowledge data that is received, and any data that is unacknowledged after a certain period of time has to be retransmitted. And the rules for how that is done is going to change slightly depending on the program, depending on the version of TCP that you're using, etc. So for things that we need time-sensitive transmission for, we can involve UDP instead. You know, we talked about how there's a lot less overhead. We don't have to check for various things, so the header is much, much smaller. So it's able to pass through and just be sent forth wherever it needs to go. It uses what's called best effort delivery. You know, I'll give it a shot, and then if it doesn't work, it doesn't work. There is no acknowledgement, and it's kind of like just sending a letter through the mail that isn't certified or registered in any capacity. It means that they're not going to bother trying to track it down if it doesn't arrive at its destination. You know, if it falls on the floor of the mail truck and then unfortunately gets swept out by a breeze, or it gets, you know, slipped under a box, or any of those stuff that can happen, and that letter kind of just goes into the ether, they're not going to be looking for it as they would for, you know, something that's like, okay, something slipped out of a courier bag that is a certified letter. We're going to dig until we find it, and then we're going to identify this letter has been lost, if it has in fact been lost, to the original sender. Now, we need to make sure, of course, that we're using the right protocol for the right application. TCP is stuff that needs to be reliable, high integrity. So databases, web browsers, email clients, these all require that the data that arrives is the same data that was sent, and the original condition is maintained. With UDP, we worry a little bit less. So voice over internet protocol, we need to just make sure that we're having a continuous stream of a given quality, and if it gets a little choppy here or there, we lose a little bit of information, don't worry about it, don't try and recover it, just keep going. go ahead and move on to the next frame. You know, just a little hiccup in the line, just keep going. Streaming live video, same thing. Now, of course, we would love it if every single packet that was sent over a stream was perfect. We were getting all the information that we were supposed to in that sequence. But in certain cases, we don't, and that's okay. What we don't want to happen is treat it like TCP, to where we're chasing down this one particular packet, and then all of a sudden we start getting more and more behind with our particular situation. You know, we're going in and we're saying, okay, live video, then we have a couple of milliseconds of delay here, a couple of milliseconds of delay here. It keeps adding up. Maybe we're on a satellite feed and it's a stormy situation like we got today. And the time delay gets bigger and bigger and bigger and bigger. And eventually we're, you know, half a second behind, a full second behind, or longer. So we start getting these weird discontinuities. That's not necessarily something that we want to deal with. So it can be a problem. So UDP allows us to skip over that. We're not going to worry about getting every last bit of data. We're going to do the best delivery effort we can right now. And in certain cases, we may not even be able to see that disruption. The amount of data loss might be something that's kind of behind the scenes, as opposed to something that's immediately visible. So TCP, of course, in order to have this reliability, has to establish a session. We have to make sure that the application at the other end is ready to receive our data, and that the amount of traffic being sent can be negotiated, meaning that if we're sending too quickly, that we can adjust and be able to reduce our data flow so that we can control the amount of traffic being forwarded. If we are going at a particular speed that is quote unquote too slow, basically the server's like, you can go faster, I can handle more, then we can work with that. And we hit that butter zone of where the sending and receiving speeds are pretty equivalent, and we're making sure that we're making the most use of our bandwidth without losing information. Reliable delivery is where we say that we're ensuring that every segment we send arrives at the destination, be it by making sure that when it's delivered we acknowledge it, or if it's not delivered, that we can get some kind of acknowledgement that it did not arrive by means of timing out. Essentially, we say, I'm going to send it out, and if I don't hear something back in 120 hops, the average time for a hop being whatever, based on ping or anything else, I'm going to go ahead and assume that that packet was lost and retransmit. Now, TCP usually uses what we call same order delivery, meaning that we number and sequence the segments in a way that allows reassembly into the proper order easily. We're not going to go ahead and worry about, you know, I have to send it first piece first or second piece second or anything like that, but we are going to make sure that once we receive a particular section, we're going to go ahead and put it in the right spot, and we're not going to worry about trying to re-receive that same item. Think of it like a jigsaw puzzle. If everything goes right, all the pieces for making the final image are in the box. It's just a matter of going through and being like, all right, well, you know, we can get some edge pieces, and then it's like, oh, this is clearly a piece of an apple, so I'm going to go ahead and put the big red pieces together, and then I'll move over to the next piece. And you just kind of fill it in, and eventually you start running out of spots where stuff could go, and things get ordered. Imagine how much easier it would be to do a jigsaw puzzle if every piece had a code on the back that told you what column and row it went to. Kind of take the fun out, though, wouldn't it? Flow control, this is going to regulate the amount of data that the source transmits, as we talked about, making sure we're not overloading or underloading the transmission line. Let's take a peek again at the TCP header. This is something we've seen before, but again, I want to talk about the various components. The source and destination port to the ID application. These are important to know, making sure that we're sending things to the correct location. Sequence number to be able to put the data back together in the correct order. And it's a 32-bit number, so it's a fairly large one in terms of file size that can be delivered. The acknowledgement number, this allows us to indicate the data receipt and readiness for the next source byte. We use what's called an offset in order to indicate that acknowledgement, so I'm sure we'll see the acknowledgement sequence in just a little bit. The header length, basically it's something within the header that says, okay, these are the pieces that we know are already here. This is how much longer this thing is going to be for these various pieces. And the reason that we have to do that is because of the options box. it has to be padded to a particular length. If there are any options, we have to have 32 bits. If we have 0 options, we have 0, blah, blah, blah. And then there are certain sequences where we use what's called padding in order to make a frame a particular size. So the header length is going to identify whether or not that options window is active or not. The control bits, this allows us to modify the purpose and function of the TCP segment. We have different flags that we can set, different parameter triggers in order to change different options about how the flag is interpreted and how the packet is interpreted. The window size is the number of simultaneously acceptable bytes. So this is where we adjust our what we call flow control. And then the checksum is what we use to make sure that the packet that was transmitted was the packet that we were intending to receive. So here we have UDP being visually described again. We reconstruct data in the order received. We do not retransmit. We don't set up a session, and we don't tell the sender about resource availability. So if the system is under a lot of stress, the only way that the sender is going to know that the receiver is having some issues is that somebody calls you and it's just like, hey, I'm kind of swamped over here. So UDP is like, I'm going to send this information to you. If you get it, you get it. That's great. If not, too bad for you. Let's try again next time. So it's what we call a stateless protocol. It's a connectionless, stateless protocol. There's no tracking. Any reliability that needs to be processed for this particular type of transmission has to be handled by the application itself. So let's say that we have multiple data streams that are being sent in a video conferencing section. Let's say that this particular web browser that we're using right now, we have a sequence where there is a chat window, and then we have a sequence that is the video stream. And that video stream has an audio stream attached to it. So the video and audio are most likely being sent via UDP. There's no error checking that's really there. If there's a hiccup and you guys get a glitch of some kind, or if I lose power and the signal cuts out, it's not going to continue to send information until it gets to the last frame that I sent. It'll get to whatever it was before the program basically experiences a cutout. Now with the data stream for the excuse me, for the chat messages, those are going to use TCP. So we can see that the web browser at this point and the application within it for Collaborate is going to use multiple substreams that will allow us to combine these different protocols. So here we can see the multiple separate communications thing I was just talking about. The port number identifiers that we use are how we manage these different conversations, to where we have currently a single multimedia interface with text, graphics, and audio that we're able to view by means of these multiplexed conversations. So when it comes to these types of transmissions, we have to think about what's our source port and what's our destination port. If we have something communicating on a web page, it's usually going to use port 80. If it's something that's using electronic mail, it depends on whether or not it's sending or receiving. Like SMTP has a different port number than POP3. Now, these source ports and destination ports are placed into the segment. Whenever we break apart the data into the individual pieces, we have this segment header that gets placed onto it. So the segment is then packeted. We add the source and destination IP, and then we're going to go ahead and frame that packet by adding the destination and source back, and then adding the trailer. So again, these processes are staggered. We're going to have a very small amount of information, and then we're going to continue to add packaging and shipping information, if you will, in order to get that from one location to another securely. Now, when we combine the IP address and the port number, be it source or destination, this creates what we call a socket. So if we have multiple processes going on the same IP, the socket process allows us to enable multiple processes to be distinguished individually. And there are expansions to those ports. So let's say that we're sending something over HTTP. If we're talking about port 80 and we have a subport of like 6, it would be 8006. in order to separate that out, and then we'd be able to actually have a sub-port within that port. Our well-known ports are going to be ones that are used for services and applications that have been reserved, so 0 to 1023. Registered ports are 1024 to 49151. So these are port numbers that are assigned by IANA. IANA and ICANN, if you recall, the Internet Numbers Authority, essentially the people who regulate who gets what IP address and all the other things. This is identified by IANA and given to the requesting entity for specific processes and applications. So certain programs will have certain default ports based on what's available and what is currently being used by the IANA assignment. So for example, program I use remotely all the time, Plex, the default is 32,400 for the port to access the local host remotely. Now, I do not recommend using the default ever for stuff like that if you can avoid it. If you can assign a port on your own, see if you can do that. Now, if you run into a problem and you have a conflict and you've got data that's getting essentially colliding with one another, then you may want to choose a different port. I usually use what's called dynamic port assignment for that, so that way it'll randomly generate a port number every time I load the program. That means that I have to use something in the 49,152 to 60. Something that's assigned by the OS and used to identify a client application during communication. So if you use something in the roughly 1,000 to just over 49,000, these are something that you can use to identify certain programs. So if you're having issues and you're concerned that somebody's maybe sniffing your traffic for an online game that you're playing, if you know what port that particular traffic is moving on, that will allow you to troubleshoot it a little bit further. So here's some example of some of the well-known port numbers, the ones that are 0 to 1024. We can see FTP here, SSH, SMTP, DNS, HTTP, POP3, IMAP, etc. You see all the different things that they do. And you can see whether or not they perform under the TCP or UDP umbrella. And for most of the well-knowns, we see that TCP is overwhelmingly used for that kind of situation. So something we can use to identify connections and try and resolve these particular protocols to what's being currently active is the Netstat command. So here in this particular screen grab, we can see that we've got C:/Netstat. And it says active connections. We've got a protocol column here, our local address with the port, the foreign address that we're trying to connect to, and whether or not that session is established. So by default, this will attempt to resolve IP addresses to domain names and port numbers to well-known applications. So again, you can see here we've got a situation with the foreign address here, www.cisco.com, the bottom of the third column. And you see it says :HTTP. Now, if it was looking at this just as a port number, you'd probably just see 80. If it was HTTPS, you would see a different interface again. I want to say that's 443. And then if you were using certain web browsers, it might actually be 8080 instead. You can see up here at the top, netbios-ssn. That's the foreign address here. So these are all showing different interfaces, possibly for the same program. If we use the -n flag for Netstat, we can use IPs and ports in numerical form. So if we don't necessarily want to resolve them to their well-known versions. All right, so let's look at 9.2. We're looking at the server communication process, making requests to a server. You can see here that we've got two clients. We've got one making a request using the source port 49152. This one's using source port 51152. And they have two different destination ports. The destination port 80 is our HTTP, that's our web access. And then SMTP on client 2, port 25, is the mail sending request. Okay, so these well-known port numbers allow us to identify what the port behavior is supposed to be. Now, the dynamic port numbers as the source port allow us to have a level of anonymity and make sure that we're not stepping on any toes as far as the well-known ports that we might otherwise be using. So the response from the server to the client then becomes this. We know that we received the connection on a particular port. That now becomes our source port instead, and then we send back using the source port from the original request. So we're just flipping it. We're just taking what was the source and making it the destination, and what was the destination and making it the source. So that way we're sending everything back to the correct connection. Now with TCP, there is a process to creating a conversation. There's a three-step process that we go through. Step one is to initiate a session with the server via what we call a synchronization request. So in the far left one, we can see a synchronization request going from A to B. Step one, send the sync. So the sync would have something like this. Sequence equals 100. Control flag equals synchronization. On the opposite side, the synchronization is then received. So that receipt means that we have to have an acknowledgement. That acknowledgement is going to say, I'm going to go ahead and send a syn/ACK request. So this is a synchronization acknowledgement. The synchronization acknowledgement is received on the opposite side, which means that we are ready to go. We have an established sequence 300 here for this, ACK 101. And the receipt on the other side says, okay, I see your sequence 300, ACK 101. I'm going to make my sequence 101, acknowledgement 301. And that's what we call the acknowledgement single. So we're going to go ahead and say sync with acknowledgement, and then acknowledgement. And we're going to see that those sequence numbers and acknowledgement numbers are going to keep flipping back and forth to increment and acknowledge what we're doing in our next step. So we see that the sequence number on A goes from 100 to 101 because the acknowledgement was 101. So we make sure that we're doing these in sequence. Again, we're having a sequence number that can be identified. In order to close this connection, and if we're creating a sequence, we have to be able to close it as well, we have to go to the opposite side, which is terminate. So we have to put on what's called the finish control flag. So that the termination request is sent by means of the finish flag. The finish flag is received. We send the acknowledgement, and then we send the final flag from section B as well. So we've got kind of a double send. And then the acknowledgement from A to B is then sent. So we have fin-ACK going from A to B, and we have fin-ACK going from B to A. So in order to end both sessions, the A and B sessions, we need 4 exchanges total. So in order to create the sequence, we need 3. In order to end it, we need 4. So the three-way handshake does a couple of things for us. We verify that the device is present on the network. We verify that it has an active service available to receive our traffic, and that we are currently accepting requests on that particular port number. Important to know. Now, in the control bits field of the TCP segment header, we have these flags that we can use in order to modify a connection based on need. There's a flag called the RST, or reset flag, that is used to reset a connection if we have an error or if we have a timeout. The control bits field here, we've seen this before. Let's go down to the fourth row. Move the column in from bits 10 to 16, or 11 to 16, excuse me. And we can see down at the bottom there is an explanation of what these different flags mean. So we've got 1 bit for each. If the bit is on, then the flag is active. If the bit is off, then we ignore it. So urgent is the pointer field that moves to the urgent field 1 row down and 16 bits over. The acknowledgement field, part of the syn-ACK that we saw there, the push function, the reset connection request, the synchronization request, and then the finish flag. So we see that the acknowledgement, synchronization, and finish flags are ones that we use all the time. So the sequence numbers for ordered delivery are assigned in the header of each packet. The first data byte of the TCP segment is recommended for the first sequence number, the ISN, giving us the starting value of the bytes. And we increment by the number of bytes that have been transmitted, so that if we have a gap, let's say that we're doing it by 100, and we've got, okay, 100, 200, 400, 500. Oop, we know we're missing 300 because that particular transmission value is not present. So we can see here that even though something arrives in a different order, if we have the correct sequence number based on those bit gaps, then we can go ahead and reorder the segment once it arrives and be able to put it in the correct sequence. We can go ahead and take, instead of having segments 1 through 6 here, it arrives as 1, 2, 6, 5, 4, 3. Well, we can go ahead and switch things around and make sure that we have the correct delivery for each one. So we got here, and I'll kind of be jumping back and forth to explain what's going on. We have a source that is transmitting 1,460 bytes of data for each segment. So if we look at the term MSS at the top in the middle column, maximum segment size. So we have A to B. The window size is 10,000. The MSS is 1460. Okay, so that means that our maximum window for transmission is 10,000. Our maximum segment size is 1460. Typically, PCB will not wait for setting acknowledgement, but that's just what we're setting up for this particular example. And that window, part of the flow control process, can be adjusted as the process goes on. So sequence number 1, 1,460 bytes, and we have to acknowledge receipt of 1 to 1,461 solid segment size. Sequence number 1461 is going to be 1,460 bytes above the last one. So we have sequence number plus MSS equals the next sequence number. Okay, so the next one up should be 2921, and then when we go up from there, that should be, let's see, 4381, and keep going on and on and on. So what we see here is we send 2 sequences. They're both received. The acknowledgement comes back and says, okay, I'm going to acknowledge 2921, which is 1 above the the top of the last MSS. That acknowledgement number now becomes the new sequence number. The window size is still good. Our send window is now 12,920 or 2920, so that's our window size. Number 2921. We're going to send that forward to 4380, and the acknowledgement comes back 4381, again 1 above the last MSS, and then the window size will adjust for the transmitted bits. So again, we're just seeing that number is going to bounce up based on that MSS at the beginning. All right, Sean said that we've got some audio bounce. Anybody else getting that? Got some UDP problems? Well done, sir.
Yes.
Is anyone else experiencing any audio issues?
Yes, it's going in and out.
Okay. Give me a second here. Let me make sure I don't have any services running in the background that I can trim out real quick. Sure, part of it's the weather, part of it's my wife running Disney Plus for my boy so that he can watch his Mickey Mouse Clubhouse. All right. Close that, close that, close that. All right, everybody. Is that any better? Is that seemingly any better anyway?
So far, yes.
So far, so good. Okay. Well, thank you for the feedback. Just make sure that, yeah, if there's something that comes up, let me know so I can go and make the adjustment. Thankfully, we're almost done with this chapter, so if there's any particular topic that you didn't catch, I'm more than happy to go back over it. So strangely enough, flow control deals with what we call congestion avoidance, and this is where we get these hiccups. So congestion, where we have too much traffic on the same conduit and it causes these collisions or loss of processing, deals with retransmission of lost segments. So if we have a situation where a particular segment gets lost, we have to identify using TCP which ones have been received and which ones have not. So if we have retransmission, then essentially we're just sending packets back onto the frame, and if we're running over too much traffic, we're still just going to make it worse. So we have to be very cautious about that. So we have to use a couple of different handling mechanisms. We have to use timers. We have to use different algorithms. And we have to adjust that flow control window to make sure that we're not overestimating the bandwidth of the receiver or of the sender. So in the graphic here, we have TCP segments 1, 2, 3, and 4 being sent. We have segment 1 getting through, segment 2's got a problem, segment 3's got a problem. The acknowledgement comes back and says, okay, I got 1 and I got 4, I didn't get 2 and 3, so we're going to go ahead and adjust the number of bytes that we send. I'm going to go ahead and send 2 and 3 again, and we'll see what we can trigger. So UDP is like, forget all that, man. I'm going to go ahead and just send this information. I'm going to get it to you. If you don't get it, well, that's a problem for you. There's no sequencing, there's no flow control, nothing like that. So that means that transmission is going to be much, much faster. It's not necessarily going to be much more stable. It just means that for what we call delay-sensitive transmissions, it's a lot less noticeable. So if there are any functions that need to be put into place that are not provided by the transport layer using UDP, they have to be implemented elsewhere, usually at layer 4. At layer 5. You have to start going into the session, presentation, and application layers. So to reassemble the UDP datagram, it's just whatever order it arrives in. So if we send 6 pieces in the datagram sequence and it sends out, and let's say we have some routing issues or whatever else, anything that we get in the wrong order is just going to be processed as is. So we have 1 through 6 here. It comes in as 1, 2, 6, 5, 4. That's just how it comes in, and then it moves on to the next sequence. So it doesn't worry about trying to re-request a packet that didn't arrive. For example, here we have a system dealing with requests for Radius, remote authentication dial-in user service. This is a very common method of remote authentication. So we have here the communication between 2 servers. We've got, or 2 hosts connecting to a server. We've got a DNS request and we've got a Radius request coming in. They're on separate ports. And they're going to process information a little bit differently. Now, DNS, of course, being more concerned about information in UDP, I want to get it quickly, more so than worrying about it arriving in a particular order. Radius, on the other hand, because it has to be very specific in terms of its what we call granularity, all the bits have to be exactly right, that's not going to use the same transmission type. So here we can see the transmissions coming across, destination and request source ports going through normally. So the verification for Radius has to be done at layers 5 and 6 because at layer 4, transport layer, that implementation is not there. So it's still going to have to verify, but it'll do it in a different method. So we can see here we've got our response ports coming across and everything is just kind of waiting for its response coming through. Now, if we use TCP and we have intrinsic reliability that's built in, this means that applications do not have to worry about handling that reliability for us. So if we go from the IP transmission at the network layer to TCP at the transport layer and everything else, we can now say, okay, HTTP, FTP, SMTP, and Telnet can all rely on the idea that TCP is going to have these particular reproducible rules. And if we have data that has to be verified, it's going to be done at that lower layer protocol. And again, that's a big part of why we do the TCP method the way that we do. We don't have a situation where we have a particular function having to be done at every layer. We do it at a particular layer that it is best suited for, and we just stay there. We go ahead and go from one to the other and don't necessarily worry about trying to reinvent the wheel. You know, something that should be done at layer 2, we're not going to redo at layer 4, layer 5, or layer 6. So applications that are suited for UDP, of course, again, the term we use is delay sensitive. So live video, live multimedia stuff that's going to be, you want it as close to now as is possible. That is going to be UDP. Simple request and reply, so things like TFTP again, SNMP, these are very minor protocols. They're sending very small packets, being able to deal with information. And then the reliability is going to be handled at that particular application layer itself. So DHCP, DNS, those will handle their own reliability sequences. IPTV, VoIP, those will just deal with making sure that you're authenticated, not necessarily with what order the bits are coming in. So that is chapter 9. Does anybody have any questions or concerns about what we just addressed? Was there anything you guys missed on the audio gaps that I need to go with you?
No, they were good.
Feeling good so far? Okay, good. All right, guys.